Welcome back. In this video, I wanted to spend a little bit extra time going over a few more examples of Lagrange multiplier problems and talking a little bit about those strategies that pop up in them to be able to solve the systems of equations. So I'm just going to go ahead and get started. Our first example here, we want to find the minimum and maximum of f of x, y equal to x squared plus y squared with the constraint of g of x, y equal to x to the sixth plus y to the sixth, which is set equal to 1. Okay. So first and foremost, I do want to kind of point out just how we know that we want to use a Lagrange multiplier in this problem. And that is when we have a function that we're trying to minimize or maximize, and then we're given some sort of constraint where the constraint here, we have the second function that's set equal to a constant. Anytime you see some setup like this, where it's equal to, not less than or greater than or anything like that, actually equal to a constant, then this should be a little flag that says use Lagrange multipliers. So Lagrange multipliers tell us that if we have this function here, we take its gradient and set it equal to some scaled version of the gradient here, so scaled by some number lambda. Then if we solve this system of equations that arises out of this, we will be able to find our minimum and maximum somewhere in the mix of those constrained critical points that we're finding. So we'll start by computing our gradient of f. And that's going to be equal to 2x to y, and then our gradient of g, which is going to be equal to 6x to the fifth and 6y to the fifth. Now, we want these to be equal to each other with the gradient of g multiplied by that scale value lambda. So that gives us matching by components our system of equations here. 2x is equal to lambda times g, so we'll have lambda times 6x to the fifth, and then 2y here matches with this one, so 2y is equal to, and then we can't forget the lambda, times 6y to the fifth. And then finally, our third equation is really just taking our actual constraint that this has to be equal to 1 into account. Okay. So our goal is to solve this system of equations. And it's going to be real tempting to go ahead and jump right in with dividing the x and the y in each of these equations and trying to simplify it down. But before you can do that, you actually have to know first and foremost that x and y cannot be equal to 0. Because if they could be equal to 0, you could be inadvertently dividing by 0 when you try to cancel the x's from each of these, or the x from each of these sides here and the y from each of those sides there. Because that cancellation process is really just division. So we want to go through and check. Suppose that x is equal to 0. Is that going to cause a problem? It actually won't. X could very well be equal to 0. Same idea here for y. And because of that, we're going to have to kind of break this up into cases. So there's no issue with x and y being 0. There's nothing to prevent that, so we need to use cases. And that's going to look like x equal to 0, x not equal to 0. So that takes care of the x's, and then y equal to 0 and y not equal to 0. Okay, so that's how we're going to approach this to round up all of our critical points for this problem. I'm going to go ahead and grab a new page for this, I think. Let's go ahead and start with the x equal to 0 case. Well, so if we fix x to be equal to 0, well, we already know, well, what x is then. So we can just go ahead and use the constraint to solve for y. This then means, under our constraint equation, which says that x to the 6 plus y to the 6 has to be equal to 1, that y to the 6 is equal to 1. And taking the 6th root of both sides, we get that y is equal to plus or minus 1. Now, I really want to stress the importance of this plus or minus thing here. This is because we took an even root here, a 6th root, or, like a 4th root or an 8th root or the square root or something like that. We know that we need the plus or minus. Okay, So x is equal to 0 and y is equal to plus or minus 1. So we're going to get two constrained critical points, 0 and plus or minus 1 for that. So two of the constrained critical points. All right, great. So that's our first case. And we've taken care of the situation where x could be equal to 0. So now we're just going to go ahead and assume that x is not equal to 0. And this means that now we can divide by x. So we're going to look back at our first equation here in our constraint, or in our system of equations that said that 2x is equal to lambda times 6x to the 5th. And I like to always try to solve for lambda first chance I get, so that way we can try to start eliminating it. And I'm going to get from there that lambda is equal to 1 over 3x raised to the 4th power. Okay, so what do we do with that? Well, a lot of times what we would do is move down to this next one, rearrange it as well, and then kind of set them equal to each other. But we're going to have a problem with that in the sense that solving for lambda here is going to require us to divide by y. And as soon as we divide by y, we are now assuming that y is not equal to 0. So we're going to actually have to revisit that working with this once we start working with the case of y not equal to 0. So anyway, all of that is to say, we've done all the work that we can by assuming only that x is not equal to 0. So now we need to go over to our cases where we assume things about y. So case 3, we're going to assume that y is equal to 0 to just kind of get that out of the way. In this scenario, we then wind up with x to the 6th equal to 1, which means that x is equal to plus or minus 1. So we now get, once again, two constrained critical points, just like we did up here. And that's going to give us plus or minus 1, 0 as two more constrained critical points. All right. And now for our fourth and final case. We could have that y is not equal to 0. And that means that we can now divide by y. So what we're going to get then is, because we had that constraint, or I keep saying constraint, equation 2y is equal to lambda times 6y to the 5th. We rearrange this the same way that we did here, and we get that lambda is equal to 1 over 3x to the 4th. Or not x, y. There we go. And so assuming that y is not equal to 0, and then borrowing this information that we had from the case where x is not equal to 0, we can now put these two pieces of information together. We have enough to be able to finish out working with both of these two pieces of information. So what I get then is 1 over 3y to the 4th has to be equal to 1 over 3x to the 4th. And rearranging that equation, getting rid of the 1/3 and moving things up to the top and stuff like that, what you wind up with is that y to the 4th is equal to x to the 4th. And taking the 4th root of both sides, we get that y is equal to plus or minus x. Okay, again, I want to stress the importance of this plus or minus here. Any time that we get rid of an even power like that, taking the 4th root, you want to make sure to have that plus or minus there. Okay, so that's as far as we're going to be able to get using those two pieces of information. It's now time to use the constraint. So our constraint says that x to the 6th plus y to the 6th is equal to 1. And we found previously that x is equal to plus or minus, or let's say that y is equal to plus or minus x. So that gives us x to the 6th. And then when I take that plus or minus x in here and raise it to the 6th power, plus or minus no longer matters. And we still have x to the 6th that's equal to 1. Combining these two pieces, dividing by 2, taking the 6th root, all that stuff, we're going to get that x is equal to plus or minus the 6th root of 1/2. Okay, great. Now at this point, it's going to be really tempting to say then that y is equal to 6th root plus or minus 1/2. And you would not necessarily be wrong, but you want to be careful in the way that you talk about that. Because what this is going to give us here, since this is a plus or minus and this is plus or minus, we're actually going to wind up with 4 constrained critical points. And here's why. If we have x equal to the positive, not plus or minus, positive 6th root of 1/2, well, we still have that y is equal to plus or minus x. So y is equal to plus or minus 6 1/2. And we have a similar case with x equal to the negative 6th root of 1/2. Y is equal to plus or minus the 6th root of 1/2. So what this means is that we basically have every possible combination of x and y with them being positive and negative. So like if x is positive, we could have y be positive or negative. And if x is negative, we could have y be, well, positive or negative. So you can go through and you can write these out for points individually, however you want to express that. But I want to show you what would be kind of the shorthand to denote that you have all 4 possible critical points. What this looks like is plus or minus. So if we want to talk about the x is plus or minus 6th root of 1/2. And then we can have plus or minus 6th root of 1/2. And what this does, when these two align, so we have the plus on top and the minus on top, and the plus on top and the minus on top, when those look the same, it means that they're either both positive or they're both negative. Okay? So this is 2 critical points, or 2 constrained critical points. The ones where we have positive 6th root of 1/2 and positive 6th root of 1/2, or negative 6th root of 1/2 and negative 6th root of 1/2. So how do we denote the other 2 options where they're mismatched? Well, we do that by taking plus or minus, once again, on the x component. And then we say minus plus on the y component. And all that means is whatever the x component is here, the sign is backwards over here. So signs match, signs don't match. This accounts for all 4 possibilities that we get out of here. And that gives us 4 constrained critical points. Okay, great. So in total, I think we have 8 constrained critical points. And to be able to figure out which one is the largest and which one is the smallest, to give the minimum and the maximum, all we got to do is plug them into that original function that we had. So we're going to plug all 8 constrained critical points into f of x, y to see which is largest and smallest. Okay, so if I take f of plus or minus the 6th root of 1/2, and then plus or minus 6th root of 1/2, like so, I'm going to go ahead and just kind of lump those into the same test, because if we look back at what our original function was, x squared plus y squared, that squared means that the sign really isn't going to wind up mattering. It's going to wind up getting canceled out when we take that squared there. So I'm just going to go ahead, whatever we get for the positive case is exactly the same as what we're going to get for the negative case. And that actually winds up being 2 times the cubed root of 1/2. Okay. Similarly, we can do same idea here for our second batch of these critical points here. So we're still going to get 2 cubed root of 1/2. All right. So now we just have to test our other 4 critical points. That was f at 0 plus or minus 1 and f at plus or minus 1, 0. So this guy right here, again, going back to our original function, we have a 0 and then 1. So it's just going to be equal to 1. And then plus or minus 1, it's going to be 1 plus 0. So you're just going to get 1. So as a result, we actually do wind up with kind of like a tie between these different points for largest and smallest. These 4 constrained critical points yield the maximums. And if you want, you can go ahead and throw this into your calculator just to check to see what that actual value is. However, I will tell you that this is just a little bit of a trick, I guess. This is how I think about it. When you take a root of something that is less than 1, it actually, oddly enough, kind of increases that particular value. So the cubed root of 1/2 is greater than 1/2. And I'm doubling something that's greater than 1/2, which means that my final value is going to be bigger than 1. Okay. And then this guy right here, or I guess all 4 of those points right there, tie for being the minimum. So that's pretty much all there is to that example. It did look, I guess, it looks pretty simple at the beginning of it. And I mean, most of the work is fairly straightforward, but it does wind up being maybe a little bit more work than you anticipate. Because of this, we went in and checked to see, okay, could x be equal to 0? Well, it turns out that yes, indeed, x could possibly be equal to 0. Same idea for y, because if we set y equal to 0, we get 0 and 0. So there's nothing there that makes that a falsehood. So we just had to be able to account for the case where x could be equal to 0, y could be equal to 0, and then you take care of x not equal to 0 and y not equal to 0 separately. And then that's what allows you to finish solving. So yeah, that's pretty much all there is to that example. Let's work another one. Okay, so in this one, we are going to find the min and max for f of x, y, z equal to 2x plus 2y plus z constrained to we're going to say g of x, y, z equal to x squared plus y squared plus z squared is equal to 9. Okay, so we have this function here, and we want to kind of constrain it to this sphere that we're working with. And again, we know that we want to use Lagrange multipliers because we have the function we're trying to optimize or maximize or minimize or whatever that has this constraint of a function that has been set equal to a number. Okay, so that's how you know we're going to use Lagrange multipliers. And to be able to do this, we just simply solve for where the gradient of f, x, y, z is equal to lambda times the gradient of g of x, y, z. Okay, so gradient of f, that's going to be equal to 2, 2, 1, and then gradient of g of x, y, z is going to be equal to 2x, 2y, 2z. All right, so let's go ahead and stack all of these into our system of equations. We're going to have that 2 is equal to lambda times 2x, 2 is equal to lambda times 2y, and 1 is equal to lambda times 2z, and then our final equation comes from the constraint. Okay. So just like last time, the very first thing we do is check to see if x, y, and z, or even lambda, could be equal to 0. So that way we can, maybe take advantage of being able to divide by x and y and z. So let's look at this and think about it. If x is equal to 0, then this side is equal to 0, and we're saying that 2 is equal to 0. So x cannot be equal to 0. Same idea here. If y equals 0, we get 2 equals 0. And similarly here, if z equals 0, we get 1 equals 0. So x, y, and z cannot be equal to 0. Also, kind of as, I guess, a bonus, lambda can't be equal to 0 for the exact same reason. Okay. So now we're ready to rearrange. I like to solve for lambda first, and then use that to kind of figure out how to get everything else. So I'm just going to use this equation right here. Since I can divide by x, I get that lambda is equal to 1 over x. And I'm going to use that to substitute into here. So let's do it down here. So we get 2 is equal to 1 over x instead of lambda in this equation here, times 2y. Rearranging, doing some canceling, all that stuff. And what we wind up getting out of that is that y is equal to x. Okay. So now we have a relationship between y and x. In our previous example, that would be sufficient to go straight into our constraint and start solving. But in this situation, we have to also get an expression for z in terms of x to be able to work with this constraint to finish solving. So we'll also look at this equation here. 1 is equal to, and then I'm going to replace lambda with 1 over x, 2 times z. Rearranging that, and you get z is equal to 1/2 times x. Okay, now we are ready to use our constraint. And I'm going to go ahead and do that on the next page, I guess. So our constraint says x squared plus y squared plus z squared is equal to 9. And we found that y is equal to x and z is equal to 1/2 x. So I'm going to swap out everything in here for x's. So I get x squared plus y squared plus, it's going to become 1/4 x squared is equal to 9, and that should be an x. So 9 over 4 x squared equals 9, which means then that x has to be equal to plus or minus, very important, 2. Okay, so here we have that y is equal to plus or minus 2 as well, because y is actually equal to x. We don't have the issue with the signs mismatching or anything like that, because we're just specifically told y matches x. And then same idea here, z is equal to, I guess, plus or minus 1 now. Okay, again, the signs agree always. So our constrained critical points then that we're going to get out of this are when x is equal to positive 2, we have that y is equal to positive 2 and z is equal to positive 1. And when x is equal to negative 2, y is equal to negative 2, and z is equal to negative 1. So those are the 2 points that we have to plug into our function f and figure out which one is going to be our minimum and which one's going to be our maximum. So we have f at negative 2, negative 2, negative 1, if we want to start with that one, I guess. And that's going to give us going back to our original function, we have it's going to be 2 times negative 2, so you get negative 4 minus 4 minus 1 is what you get from that. And that gives you negative 9. And then f at 2, 2, 2, we're going to get 4 plus 4 plus 1, which is equal to positive 9. Well, that's pretty clearly going to be our minimum, and this is going to be our maximum. And that's pretty much all there was to that problem. That was pretty straightforward. Okay, our final example is going to be one that's a little bit more involved. We're going to do a 2 constraint problem. So I'm going to focus primarily on the setup, and then I'll probably leave a lot of the algebra at the end, just plug and chug type algebra, not anything too terribly difficult at the end. That's going to be for you to do. So in this example, we are going to find, I guess in this case, we'll just find the maximum value. We'll just focus on that. Of f of x, y, z equal to x plus 2y plus 3z. And we're going to have this be subject to 2 constraints. We're going to say g of x, y, z equal to x minus y plus z equal to 1. And h of x, y, z equal to x squared plus y squared equal to 1 as well. Okay. So when we're working with these kinds of problems that have 2 constraints, we can still use Lagrange multipliers. We just have to kind of generalize it a little bit. We still have this idea of the gradient of f, and that is going to be equal to lambda times the gradient of g. And we also want to include this guy right here, so we'll just multiply it by a different number. We'll call it mu. Oops, that should be a gradient. Just like so. And then this is going to give us a system of equations to solve. So gradient of f, x, y, z is equal to 1, 2, 3. Gradient of g is equal to 1, negative 1, 1. And then the gradient of h, x, y, z is equal to, we'll have 2x, 2y, and then there's no z in this equation, so we're just going to get a 0 there. Okay, so this gives us the following system of equations. We have 1, there it is. Okay, is equal to lambda times 1 plus mu times 2x. And then 2 is equal to negative lambda now plus mu times 2y. And then finally, we have 3 is equal to lambda, plus 0. That is quite convenient. And then our last 2 equations are going to come from our constraints. X minus y plus z is equal to 1. And x squared, let me make this a little bit longer, plus y squared equal to 1 there as well. So, well, one thing that's really convenient here is that this lambda here, we know lambda is equal to 3. That is super, super nice. And the reason for that is we now know that mu can't equal 0. Neither can x nor y. And why is that? Well, instead of lambda, let's put a 3 here. Okay, so if mu is equal to 0, or if x were equal to 0, we would then have 1 equals 3. Well, that's just silly. So mu and x can't be equal to 0. Same idea here. If y were equal to 0, we'd have 2 equals 3. Equally silly. So the fact that lambda is equal to 3, we're able to deduce using these two right here that mu, x, and y cannot be equal to 0. Okay. Now, that might beg the question of what about z? Well, we actually don't really need to know whether or not z can be equal to 0 because as you go through the problem, you'll see that we're never going to wind up dividing by z. So just kind of focus on this piece right here and the rest of it will pop out. So since we know this, what we're able to do is take these two and kind of rearrange them, I guess. If I get, so I'll have, now my goal is to just kind of try to eliminate mu, right? So we're going to solve for mu and then put some pieces together and do that. Or actually, you know what, I take it back. Let's use a little bit of a different approach this time. I want to kind of show you a different technique. So with this one, what we're actually going to do is find an explicit value for mu. And then what we can do is use that to plug back in and solve for x and y. Okay, so what do I mean when I'm saying that? What I mean is that, so we have this 1 is equal to 3 plus, let's say 2x mu. Well, what this means is I can rearrange x for x in terms of mu. When I do that, what I'm going to get is x is equal to -1 over mu. Okay. And then I can do the same idea on my second equation, 2 equals -3 plus 2y mu, which is going to give us that y is equal to 5 over 2 mu after you rearrange that. Okay, I'm going to continue this on the next page. At this point, I can actually use a constraint to figure out what mu is, okay? So we have the constraint x squared plus y squared is equal to 1, and we're figured out that x is equal to -1 over mu, and y is equal to 5 over 2 times mu. And we can make these substitutions in here to solve for mu. So we get -1 over mu squared plus 5 over 2 mu squared, and that's going to be equal to 1. We can solve all this out, rearrange it, combine like terms, all that good stuff. What you wind up with at the end there, though, is that mu is equal to plus or minus the square root of 29 over 2. Okay. So kind of like substituting this back into these two expressions right here, we get that x is equal to, it's going to be flipped from whatever mu is. So I'm going to denote that with a minus over a plus of, and then it's 1 over, so 2 over root 29. And then y is equal to, it follows the sign of mu. So it's going to be plus or minus 5 over root 29. Like so, is what you're going to get out of that. Okay, so now at this point that you have values for x and y, you can plug these values into your other constraint that we have not used yet, which is going to be the x minus y plus z equal to 1, and solve for z. And then after that, you would plug the constrained critical points that you found into f of x, y, z to see which is largest. So honestly, now that we have x and y, and actually, frankly, after we had mu, it really just kind of becomes a lot of brute force plug and chug type stuff. So I'm actually going to leave that part to you because that's actually all really quite straightforward. You just take these values, plug them in here, solve for z, and there you go. There's a couple of cases that you have to consider, you know, the minus and then the plus and then the plus and then the minus for the x and the y. So you get a couple of values for z there. But I think at the end, what you should wind up with is 2 constrained critical points that and one of them is going to be a larger value, which will give you your maximum. So that's pretty much all there is to that. It actually solved quite nicely due to the fact that we had this information that lambda would be equal to 3. And then after that, it's just a lot of maybe some messy algebra, but it's not a big deal. So anyway, hopefully this has been helpful, kind of an assortment of different styles of problems that you can do for Lagrange multipliers, and then also introducing a little bit of a new technique that you can use to solve. But yeah, that's pretty much it for this video. I'll see you next time.